Hello, my name is John Bozart, and this is my Physics 2211 Lab 2 on the motion of a falling object. The goal of this lab is to choose an object that falls somewhat slowly to the ground and analyze its motion, taking into consideration how the forces of gravity and drag affect its position and velocity. My object is a slightly crumpled paper ball. Utilizing Newton's second law, also known as the momentum principle or change in momentum over change in time, the position and velocity update formulas can be derived. To incorporate the different forces acting on the paper ball, the formula is Fd equals b times the magnitude of velocity squared times j hat, and the force of gravity equals negative m times g will be used. B is the coefficient of drag, and j hat is the direction vector that points opposite of the force of gravity. Using all of these formulas and the knowledge that F net equals F drag plus F grav, two different computational models can be produced and compared to an observed model of the ball's motion in Tracker. One will be the position based solely on gravity, and another will be the position influenced by both gravity and the force of drag. Here's my tracker analysis, in which I set the coordinate axis origin at the center of my ball and align the y-axis with the side of my closet. I drop the ball from around 5 feet, and as the video plays, you can see the ball of paper begins to shift to the right in the positive x direction. The effects of this movement will be discussed later in the conclusion. Here's my plot of y position versus time and the data points that will be used to compare the various models. After taking data from Tracker, I implemented it into the Glowscript code for gravity only. As you can see, the mass of the ball is 0.004 kilograms, the diameter is 0.0762 meters, and the initial and final positions are 0, negative 0.02, 0 meters, and 0.147, negative 1.539, 0 meters, at t equals 0 and t equals 0.567 seconds, respectively. Using the formula seen earlier, the force of gravity equals negative m times the gravitational acceleration on Earth, g, which is 9.8 meters per second squared. As seen in the code, this weight force is equal to the net force, and the velocity and position vectors are updated while the time is less than t equals 0.566 seconds. Because only the force of gravity is being analyzed, the drag coefficient b is set to 0. In addition, the arrow scale formula is shown to be 2 times mass over the absolute value of the force of gravity. Although the code for the arrow's axis and position is correct, I believe my object's mass is too small for the arrow to be present in the model. In case you want to take another look at this code, the link is in the description of this YouTube video. If the code is run, you can see that the object moves downward at positive acceleration. I will use these data points later to form a graphical comparison between the Tracker model and this force of gravity model. Now, shifting to the Glowscript code that includes both drag and weight force, we see that the net force equals Fg plus Fd. The addition of drag force requires the calculation of the coefficient of drag, denoted by b. This value is found by repeatedly running the code until the computational model's final position of the ball matched that shown in Tracker. The arrow scale for drag was also added, so that an arrow would be pointing up while the arrow for Fg is pointing down. Running the Glowscript code produces this model that shows the ball moving with similar motion downwards. The data below will be used to plot a position versus time graph on top of the gravitational force comparison previously mentioned. The graph on the left shows the relationship between the y position and time when the force of gravity is the only force present. The predicted series shows a larger final position than the observed because it does not account for drag. The other discrepancies between the two curves are most likely due to another force acting in the positive x direction, such as a light wind. In addition, the video could have been shot at an angle, so the y-axis might not be completely vertical, and the computational model could have overpredicted the y position. On the right is the ball's y position versus time graph when both drag and weight force are in effect. The new gray curve that represents the addition of the two forces closely resembles the gravity curve, except for the last 0.2 seconds when drag starts to occur. Overall, the model including drag and gravity is closer to the predicted model in Tracker than that of just gravity because drag is in the positive y direction and provides a more accurate description of the paper ball's motion. Terminal velocity occurs when the force of drag pointing up equals the force of gravity pointing down, meaning that the net force on the object is 0 and it is experiencing constant velocity. The velocity versus time graph for the model without drag shows constant acceleration of 9.8 meters per second squared, which means that there is not a 0 net force and that terminal velocity is not achieved. The model with drag on the right shows that velocity beginning to flatten out horizontally, which implies that constant velocity was close. Although terminal velocity was not reached, if I had dropped the paper ball from a higher initial position, the drag and gravity forces would have eventually equaled out and terminal velocity would occur. If I had thrown the ball downwards at a velocity of 1 meters per second and held everything else constant, the terminal velocity would not change values, but would be reached quicker. The drag force increases as speed increases, so if the initial velocity was raised, then the drag coefficient would change proportionally to result in the same terminal velocity. Thank you.